Hey guys, we are the USSF Heavy Lift Morphing Drone Black Team from the UCF Senior Design Group. Now, the growth of innovation in rotorcrafts has allowed the mass use of drones in everyday life. From hobbyists zipping around their little RC drones in races, to farmers utilizing heavy lift drones to maintain their crops, the capabilities of rotorcrafts are growing every single day. Now, what's not so common, however, is a drone with a heavy lifting capacity that is foldable and also relatively easy to carry around. Usually, heavy lift rotorcrafts have fixed arms and a heavy weight, making them not convenient to move around. Now, our project, codenamed Morpheus, serves the purpose of a heavy lifting quadcopter with the foldability convenience that's unconventional with normal commercial drones.
The United States Space Force proposed the Rocket Vanguard project, in which rapid global response will be administered through a large-scale rocket, where payloads include multiple cargo containers called TEUs. Within one of these containers, the Morpheus drone will be deployed and be capable of hoisting other full-weight cargo containers for distribution to its needed locations, significantly reducing the amount of manpower required for such a task. The proposed Rocket Vanguard project will be used to innovate rapid global response to natural disasters and change the impact of first responders. The full-scale Rocket Vanguard project proposed a container size of 8 by 8.5 by 20 feet, with a maximum weight of 17 tons. The prototype Morpheus is built in a 1/14 scale, where the container dimensions are 6.85 inches by 7.26 inches by 17.14 inches. And our required maximum payload is going to be 12.4 pounds. You can see the container dimensions with this container that we built right here. The internal dimensions are going to be the 14 scale. In order to accommodate the heavy payload capacity with a compact shape, Morpheus has 24 times size increase, which allows larger propellers to accommodate for thrust requirements.
So the scope of this project is to be able to create a rotorcraft that can accomplish the following four goals. Firstly, with all the components attached, the drone should be able to fold and fit within the dimensions of the container. Number two, the drone should be able to create enough thrust to both lift and maneuver the drone with and without the payload. Number three, the drone should have a cargo attachment system that allows for quick attachment and detachment of the payload. And number four, which is the ultimate goal, the drone should be able to lift and deliver a cargo of 12.4 pounds within a specified distance.
The team began by coming to a consensus on the building of a quadcopter, in which the trade-off between the propeller size, foldability, and stability deemed best fit for our application. With the decision of a quadcopter design and all our project goals determined, the team began component design. The arms of the quadcopter were designed using CAD. Initial designs included the use of cylindrical and rectangular arms, as well as the consideration of fixed versus extending arms. For maximum foldability and thrust reduction, the team went with an extending arm design, with the inner arm having an I-beam cross-section to support the force that the outer arms will produce on them. Validations using FEA and modal analysis showed that the possible failure points were located at the point of contact with the frame, as well as where the motor would mount to. Redesigns using reduced sharp corners and supported geometries to allow for mitigations of these failure points.
Now we're going to talk about the central frame and the cargo attachment. So the central frame is going to be the house of the electronics. All the electronics components are going to be sitting on the central frame. So we're going to make sure that there's no interference on any connection. We're going to have the battery, we're going to have the flight controller, the ESC, the radio transmitter, the receiver. Everything is going to be connected together. So we're going to make sure that all those connections are not going to be there's not going to be any interference on there.
With most of the other components being commercially acquired, the arms and central plates are the only fabrication required for Morpheus. With the complex geometries of the arms, use of carbon fiber would not have been feasible. Thus, we decided to manufacture the arms by 3D printing with Bamboo Labs carbon fiber PLA. The carbon fiber PLA is stronger than normal and has a higher melting point than typical PLA. The central frame plates were considered to be constructed out of balsa wood or carbon fiber as well, but the selection of carbon fiber PLA overruled these in terms of cost, strength, and manufacturability. The modulus of rigidity, yield strength, and melting points of the carbon fiber PLA all fit requirements for Morpheus. With the extending arm design, the team is able to use larger rotor blades. Initial plans to manufacture and validate our own propeller were scrapped in favor of commercially available propellers. Utilizing a folding propeller, a propeller of 20 inches was chosen to create the sufficient thrust needed. To account for the high torque that would be required from the motor to spin such a propeller, the team chose the 505ST motors, which were within the RPM and torque specifications that were needed. The team required a battery that had a sufficient voltage and discharge rate to maintain power to the system. The selection of a 6S 22.2 volt 5200 milliamp hour LiPo was chosen to power the drone with an expected runtime of about 2 minutes. The flight controller and electronic speed controller must be compatible with the protocol that is received on the receiver. Morpheus utilizes a SpeedyBee F405 V3 flight controller and a SpeedyBee BLS 50 amp ESC. The transmitter and receiver are a FR Sky Tyrannus QX7.
The team conducted extensive testing alongside simulations in order to validate the design. The expected load of each arm is approximately 2,000 grams of force for a total of 8,000 grams of force. Using FEA finite element analysis in SolidWorks, an overall load of 12,000 pounds of force was applied to the ends of each arms where the motors mount to observe deflection of how the arms would react under force. The tip of the arms deflected approximately ½ an inch, which is very reasonable within this design. It clears every area where any impact may or may not happen. The observed stress was well within the threshold of PLA as well, so we won't observe any breakage or permanent plastic deformation. Minor stress was observed at the tips where the arms mount to the frames, but that was nominal. The initial bench testing was done on the arms for deflection test, where we mounted the arms into a frame and pulled up on it using a scale to observe the deflection of the physical test, which also coincided with the FEA analysis performed in SolidWorks, where about 3,000 grams of force was applied and we observed 0.55 inches of deflection. We also did a dynamic arm test where we had the arm mounted to the body and the body was secured to a surface. This way we can observe any vibrations and the physical deflection of the arm that can occur during the flight. We ran the motors up to 100% at one point and it happened successfully. We ran the motors on another test as well, and at 60% the initial arm design failed and it sheared off at the tip where the motor mounts. We needed to do a redesign, so we ended up also printing it in a different fashion because we initially had it printed in a vertical fashion, so the layers ended up separating, causing our failure. With the redesign, we rotated the design 90 degrees during printing, so the layers will not separate vertically, but they'll be stronger in the vertical direction. And we conducted these tests again, and we're very successful on those as well.
An important aspect of creating a drone is to back up conceptual designs with CFD simulations, specifically where the propeller is involved. All simulations for the propellers were created with the Siemens program SimCenter Star CCM+. The blade element method was used to accurately replicate each propeller as a virtual disc. 3 simulations were performed: single disc, 4 discs, and 4 discs with the full body. The single propeller simulation produced a thrust value of 50 newtons, which was roughly 0.5% less than the expected thrust value. The following 2 simulations showed consistent thrust results for all 4 propellers, and the influence of the other propellers and the body of the drone did not have a large impact on the behavior of the propellers. Thrust production bench testing was completed by the team using a pivot rig and a kitchen scale as our thrust stand. Thrust tests were completed on a 15.5-inch propeller, as well as our 20.5-inch T-motor propeller. We completed testing with the KDE 4012 motors, which were not rated to handle the loads of the 20.4-inch propeller. This resulted in the motor reaching higher than normal operating temperatures. However, thrust values of 3960 grams were recorded, which seemed promising considering that these motors did not have the rated torque to support these propellers. The result leads to the conclusion that pursuing a motor rated for a larger torque value would be beneficial for our project.
The team had begun initial electronics assembly using the SpeedyBee F405 V3 flight controller and the BL50 amp ESC, as well as the Spectrum DX6E transmitter and receiver. Signals sent from the transmitter would be sent from the receiver to a PPM encoder in order for the flight controller to combine the multiple input signals to one. Initial firmware flashing and PID configuration for the flight controller was done through the Betaflight software. Motor connection wires were soldered and connected to the motors using bullet connectors. The team had begun initial assembly testing by spinning the 4 motors was done through the Betaflight software. Attempts to idle spin the motors using the Spectrum and PPM encoder were unsuccessful, as there were induced vibrations which came from rapidly alternating amperages to the motors. The alternating current was deemed coming from noise in the system. The initial assumption was that there was frequency interference from the PPM encoder, so the team switched from the Spectrum and PPM encoder to a FR Sky XQ7 transmitter that utilized S-bus receiver protocols. Idle spin tests again demonstrated the jolting of the motors when input was received from the transmitter. The issue lied in the mechanical noise that was created from the vibration in the unsecured flight controller. Bolting down of all components eliminated the presence of the vibrations, and with that, Morpheus was ready to begin flying. Initial flight tests were performed without the payload attached. A hover of roughly 12 inches was sustained on multiple trials with controlled landings. There was a non-induced yawing limit that was not eliminated with the use of the transmitter trim. Also, the drone was shut off after some trials, requiring us to reboot the flight controller and rearm the motors. The team is currently working on iterations of PID tunes in order to eliminate the yaw moment and sustain equilibrium in trim upper flight. Investigations into any shortages in the ESC that can result in underpowering of any channels are also underway, as well as the addition of a new appropriately sized capacitor for the ESC board to collect any surge amperage, as this may be a cause for sudden power downs.